Now, you may still be a little concerned. I've tried to show you that using this environment model, we can see how the computation of a recursive function should do the right thing. But you may still be saying, wait a minute, does this really work? How do we know that our recursive code will work? And when I say will work, how do we know both that it's actually going to stop, and how do we know that it computes the value that we want it to? So I'd like to walk you through that a little bit, just to give you a sense of how we can reason about it. And let's start with the iterative version. Itermul, we know terminates because b starts out initially positive, and each time through the loop, it decreases by 1. And just by simple logic, if it starts out as a positive or non-zero, non-negative value as an integer, and we keep decreasing by 1, at some point it's going to get down to 0, which was our test case, and it's going to stop. Great. Now, what about for recursive mul? We can actually reason about it in a similar way. We know that recursive mul, if it's called with b as the value of 1, stops, because there's no additional work to do. The code simply said return a value, so we know it stops, and we also know it gives us back the right value. What else do we know? Well, we know from our code that if we call recursive mul with an integer bigger than 1 as a value of b, it makes a recursive call with a slightly smaller version, in fact, b minus 1. But by exactly the reasoning that we just used here, we can apply the same argument to that call. It's going to make a recursive call with a smaller version of b. And because b is reducing by 1 each time, started out bigger than 0, eventually we have to get to a place where it has a recursive call with b equal to 1, which says we're going to get back down to that case, and we're going to stop. Great. So we know it stops. How do we know it does the right thing? Well, we're going to come to that. And to do that, I'm going to borrow, with a little bit of a side tour, a tool from mathematics. Because in fact, what we can do is we can use the idea of mathematical induction to reason about code. What's mathematical induction say? Well, if you haven't seen it before, here's a simple definition. If we want to prove a statement, a mathematical statement, that is indexed on the integers, that is, it's a statement where one of the parameters is an integer, if we want to show that that statement is true for all values of n, here's how mathematical induction works. We're first going to prove that it's true for n's smallest value. It will typically be when n is equal to 0 or n is equal to 1. And then we're going to prove that if that statement is true for an arbitrary value of n, you can show that it must be true when n is 1 bigger. If we can prove these things, we can prove it's correct for small values, and we can prove that given any value, it's true for the next larger value, then induction says we can assume it is true for all values of n. That's powerful because it's a way of helping us deduce that our code, if we can use it there, works all the time. This may sound a little funny, so let's look at a very simple example from math. And here's the simple example. If I add up all the integers from 0, 1, all the way up to n, the claim is that that is equal to n times n plus 1, all divided by 2. It's a little statement of fact from mathematics. But let's see how induction would actually let us prove that. So if we wanted to prove it, what do we have to do? Well, we got to look at the base case, the simple case. If n is equal to 0, what do we know? Well, this left-hand side of that equation is just 0, so that's done. And the right-hand side, I'll substitute in, if n is equal to 0, that says 0 times 1 divided by 2, well, that's 0, so we know it's true. Okay? The inductive step says that we need to now assume that this statement is true for some value. Let's call it k. And what we need to then show is that, as a consequence, we can also establish that it's true for k plus 1. So we're assuming it's true for smaller versions of the problem, and we want to show it's true for the next larger version. If we can do that, then we can assume it's true. We can prove, in fact, it's true for all values. So what do we need to do? We need to show that this is equal to that. Okay, but this left-hand side, that is just the same as taking this part, plus k plus 1, and that part we've assumed is true. That was part of our assumption. We said it's true for smaller versions. So we know by that one that that is given by this definition. So that is simply this plus that. Okay, that's nice. And then I can just do a little bit of algebra. I'm not going to do it here, but if I just do the additions together by a little bit of algebra, I can show that this piece here becomes that piece. And And that's exactly what I wanted to prove, because this is just that definition where n is equal to k plus 1. What have I done? I've said, I show it's true in the simple case, and then I said, let's assume it's true for all cases up to some size. Given that, I can prove it's true for the next larger case, and by induction, I can assume that it is true for all sizes. Great. What does that have to do with code? Well, the same logic applies to code. There's my recursive mul, and let's look what we have. We have, in the base case, we can show that recursive mul stops. If b equals to 1, it just returns a value, and more importantly, it gives us the right answer. It gives us back a. Okay? A times 1 is just a. And then what do we know? In the recursive case, we can assume that recursive mul correctly returns an answer for problems of size smaller than b. And then what do we know? Well, by this step right here, we know that this is not only going to give us an answer, it's going to give us back the correct answer for a times b minus 1. And therefore, we can assume, or not assume, we can deduce that this will return an answer, because it's just doing an addition, and it's giving us back the right answer. So it must give us back a correct answer for a problem of size b. And therefore, by induction, we've just shown that this code always stops and returns a correct answer. And when I say always stops if we give it an appropriate value for a and b. We're not going to do a lot of proofs throughout this course, but this is one nice way of seeing how thinking recursively actually works very well, and we're guaranteed, if we do it properly, that it will give us correct answers and it will terminate.